Okay, so I'll be speaking about the Markov switching GARCH model. So here we have a stock return series, and one of the key things to do when you have stock return series is to model the volatility. So what we can see from this series is that we have some features of stock returns. So we have some kind of clustering. So when the volatility is high in day t, well, in day t plus 1, the volatility will probably be high again. So some people have developed a model that capture this kind of feature, such as the GARCH type model. So you have YT, which is distributed with zero mean, some volatility variance HT, and some Xi shape parameters. So the model is pretty simple. You have an omega, and it's a function of the past return square and the past variance. So when we fit this kind of model to real data, what we observe is often that the alpha plus beta will be above 1 or very near to 1, which say that we have a lot of persistence. So the shocks stay there for a long time, which is not quite realistic. And if it's above 1, well, it say that the model is not, well, the variance goes to infinity as time goes, which make less sense. So some people argue it's long-term model, and others argue that there's structural break in the volatility. So to test this, well, we simulate two GARCH model with the left side is the right side for you is a low volatility state, and the left side is a high volatility state. So we simulate this model, this model, and we fit a GARCH model on this. And what we see, well, alpha plus beta is above 1, which means that as time goes, volatility goes to infinity. So structural break brings this kind of behavior of the GARCH model. So what we do, well, we add structural break, switching into the model. So it's the same model, but now the volatility, the distribution, the variance depends on the state parameter k. So it's the same model everywhere, but you have a subscript k everywhere, which can be modeled quite easily, and it's tractable with the model of AS and all 2004. So I was quite interested in this model, so I went to CRAN, and there's no package dealing with that, so we created one. So the MSGARCH model, well, in a nutshell, k-separated single regime conditional variance process, possibly k-separate conditional distribution. You can have the same shape parameter by state, or you can switch them if you want. Markov chain rules the switch between the regime, and we assume a zero mean process, so the mean has been removed from the return process before modeling the volatility. So everything is in C++ thanks to our CPP, because the likelihood is quite expensive to compute. The estimation and the fitting process is a lot like useR, if you ever use this package, which is the package that usually people that fit this kind of model use in R. And then we have a lot of functionality for simulation, model selection, a risk measure forecasting, and the visualization. So this is all the single regime that we call model. So we have the that we have implemented. So we have the MSGARCH, which is the model that I've shown you, and a lot of variant of this model that account for asymmetry in the stock return. Asymmetry means that, well, if there's a negative stock return, well, it will affect the volatility differently as if there's a positive shock to the return. So we have the eGARCH, the GGR, the TGARCH, and the new GAS model. We have a lot of distribution that are commonly used in financial data. We have the normal one, the student T, and the GED distribution, as well as skewed version of them with the Fernandez and Steele transformation. So the first step when using our package is to create a specification. So you input your model, your distribution, do skew if you want. Is it a skew distribution or not? Do mix is if you want to constrain the Markov switching the transition probability matrix to have a mixture behavior instead of a Markov chain behavior. And do shape in is if you want the shape parameter to switch with the parameter from your volatility model. So example, we have the simple GARCH model, which I've shown you previously. We have the two-state MSGARCH model, which is two single regime GARCH model, but with the Markov change that rule the switch between them. And we have a complex model with all sort of the variance model and every state that are different, other different distributions, skewed or not skewed. So if you want to do like crazy type of model, you can do it also. So what's inside of a specification when you create it? So it's a S3 class. With inside is embedded a C++ object that is templated because we use templated object for extension, which is very nice in this kind of model because it's kind of building blocks everywhere. So for example, we have the class normal, which we don't know, it can be symmetric or skewed. So we have the class skewed also. That takes an underlying, which is one of the distribution, normal, student T, or GED. And then we have a class of model, a variance model that, in this case, the sGARCH would take a distribution. And then we have the single regime class that have all the functionality to calculate the likelihood, do the filtering of the conditional variance, and that take a model. And we have, in the end, the Markov switching class, the MSGARCH, that take a vector of single regime object class. So if you want to do a new distribution, for example, we just implement a new class of underlying, and it will work out of the box very easily. And same thing for it with a model. Well, there's nothing else. There's skewed and symmetric. There's nothing else behind this, so this will stay the same forever, probably. So a little illustration. So we have here the SMI log return, the Swiss market index log return from 1990 to 2000. So we create a model, the spec, which is the same one as this one. So a two-state JGR with student T skewed distribution in each state. So we fit this model with fit.mle for the maximum likelihood estimation. And then we get our output, out.mle, which we have our fitted parameters, our transition matrix, the state probability, the long-term probability to be in this state, the unconditional volatility in each state, and then information criteria and the log kernel. So what we can see is that the parameters are quite different from a state to another, and then since we have a high probability to stay in each state when we are in this state, it's very persistent, so the switch doesn't happen often. We can do this with a Bayesian estimation too. We use adapt MCMC to fit Bayesianly. So with fit.base, the same kind of output, but with the posterior mean and the posterior transition matrix. So when you fit your model, now what can you do with it? So we have the filter volatilities, filter probabilities. We can simulate ahead of like the last day of your data, which can be nice to make n-step ahead forecast of risk, for example. We have the predictive density, risk measure also, and the information criteria. So everything is compatible with MLE or Bayesian estimation, of course. So for example, for the filtered volatility, at the right, the top right, we have the state 1 volatility. At the bottom right, we have the state 2 volatility in time with the model that we have fit previously. And for the state, the filtered probability to be in each state, well, the left, top left is the state 1 and top bottom is the state 2. So can I have the, oh no, it's not this. Doesn't work? Okay, I will go with the mouse. If I can. Okay. So here when we switch to state 2, what we observe is that we switched state also. So this was indicated by the fact that when we check the unconditional volatility of state 2, well, it was higher. So when we switch state, well, we'll have a higher volatility in this fit. So we have the pred, which is like the predictive density. You takes an object parameter, which can be a fitted object or a specification You can provide x, which is the value that you want to evaluate, the theta, which is the parameters, the y if it's your series, the log if you want the log predictive density, and do.ids is an option that we have in almost all the functions. Is that you want to do it in sample, so we filter and we give you the density at each time in your sample, or you want the one at t plus 1, the last one, the predictive one. So you can add the log. With this, you can export the log likelihood function that we show on the bottom right, or if you want to include the priors in there, you only use the kernel function. This side. So an example of the predictive density. So we want the predictive density at time t plus 1, t being the last data or data. So we fit with MCMC and MLE, and we get those distribution on a grid of X, which show that, yeah, it kind of make a difference which way you want to fit your data, whether you want to use a maximum likelihood estimation or a Bayesian estimation. So this is nice since you can extract from this all kind of risk measure and all kind of fit, goodness of fit data. You have the risk function also, which the same as the pred function, same kind of input, except we have the level that is added there and the ES, which is for expected shortfall. The level is like, do you want like 95% value at risk, which is like, value at risk is simply that you have, if you have the 99% value at risk, well, there's 1% of chance that you will have a return that is below this value at risk that you find. So again, we have do.ids equal true or false, which is you do one in sample or the sample. Here we do it in sample and we plot our series too. So again, what we see is that if the return seems like very volatile, well, the value at risk will go up, down quite a lot, which means that you have a lot more risk at that point in time. So what's next? Well, we have a Google Summer of Code project for this year. This was the result from the Google Summer of project of 2016. We do it again this year with Leopoldo Catania, which is working right now on this to add much more functionalities. We have a working paper that demonstrates like, is it really worth it to implement this kind of model for real data? So we compare single regime model to Markov switching model, and we have some nice results in there. We do a large scale study of over like 500 asset type of asset. The wish list that we want to do for this year, at least for the end of August, is have improved starting value strategy for faster optimization, multi-step ahead forecast, which we already have, parameter constraints, so if you want to constrain your parameters somewhere, well, you can do it. Standard error estimation for MLE at least, because we got asked this question a lot. We're Bayesian guys, so we use the chain to estimate our errors. So custom MLE or MCMC optimizer, so if you don't like our stuff, you can do your stuff. And multivariate model with regime switching copulas, which is a big one that we want to. And more as we think about new ideas. A lot of them are already implemented in the GitHub version 0.19. The CRAN version is currently 0.17.7, which I would like to recommend, but I don't recommend. If you want to work with the model, you should go with the GitHub version, because we are waiting for the end of the Google Summer of Code before putting the new version on CRAN. So it will come with new documentation because we have changed a lot of stuff, but it will be better, of course, than the current version. So thank you, and if there's any question.
Yeah. Do you plan to give the possibility to take outside information in order to forecast the Markov chain on switching states, because the switching states can be due to market information. I mean, if you have a
do we plan to input like external variable that can like move the probability to switch from a state to another? I want to do this, but I have some resistance from my other partners. So because it's kind of a heavy modification of the current code. I think it will be interesting because there's nice research that can be done with this kind of flexibility, but probably not in August. Maybe if I have time, I will try to put it in there somewhere, and it could be nice.